Okay, the second speaker of today is Aaron Young, who will talk about star formation models in the ultra-high redshift universe inspired by 2 years of JWST observation. So thank you, Aaron, and the floor is yours.
Reading that out loud. I'm going to joke about it. I was told not to joke about things, but I will have to joke about it. Hi, so my name is Aaron Young. I'm now a postdoc at Space Telescope Science Institute. 3 years in a row coming back. Thank you for inviting me back. So this is the title I submitted to Avishai a few months back. That was what I was working on a few months back. But, you know, things change course. Not all science is fleshy. I wish I could present to you a new model that explains everything, but it turns, the journey turns into some soul-grinding, self-doubting, troubleshooting, debugging, and this is where we come to now that, and why we might not need one with a big might. And, you know, spoiler alert at the end, we probably still need it, but not as much as we thought we needed. Okay, so let me just quickly recap how did we get here. So this plot you saw yesterday, the gray band is the number density of galaxies measured by a few JWST programs. These are the ones I'm involved in, but I'm sure the other ones like Cosmos Web also do their measurement, and this is basically where things are. The lines are theory. They are a bit all over the place. Seneca Sam stands here. It goes down here. It's somewhere in the middle among all the simulations. It's in log scale, so it's hard to, you know, do this just by eye. But they are all over the place. The Seneca Sam is not the worst, but also is not up there. So we thought, okay, well, at least we're somewhere there in agreement with the rest of the simulation. So we kind of accepted this. So we see this coming. This mismatch of the theory predictions versus the actual observations. We probably didn't see this coming because I wrote a whole series of papers based on the Santa Cruz SAM, which I'll tell you what it is in a bit. And we thought we have a pretty good shot of understanding how the universe works, how galaxies form over time. Despite we stopped at redshift 10, and the model performed quite well there, we don't think it would come up with this huge discrepancy at redshift 11, 12, and 13, 15. So for those of you who are not familiar with this model, this is the Santa Cruz SAM, which it was born here when Rachel Somerville was a grad student with Joel. And then she went on and continued to develop this model. And then I became a student back in 2014 and started using the model and use this to produce predictions for JWST mainly and start to adopt it for roaming. So it's a SAM which we don't track particles or grid cells. Instead, we curate a set of physical processes that we think have leading effects on shaping galaxy properties and their evolution. And then we use that to track millions of galaxies over time on a laptop. So it's a great tool for controlled experiments where we can switch out individual model components and understand how they affect galaxy properties. You know, in large ensemble galaxies. So there are a few pros and cons of this type of model. It's perfect for what I want to achieve, to do. And at the end, we also use the predicted star formation history, and you know, we couple that with SED and then evolved it into either rest frame, observed frame, and get geometry. So we go all the way to things that we can directly compare with observations. So we have a pretty good, promising starting point. So the first thing I did is to check the model's performance at redshift 4 and beyond, and it's in this, you know, if you remember this from previous talk, I showed this three years in a row. So the scalar mass function shows that without any need of dust, the predicted evolution of scalar mass by the SAM can naturally reproduce the observed evolution out to redshift 8, and this was Hubble's time. So these are Hubble observations. And with star formation rate distribution function, it's a similar story. It reproduces the evolution. We have to put in a certain amount of dust to reproduce the evolution in UV luminosity. So this all looks pretty good out to redshift 10. And so we thought we had a pretty good shot, and we wrote this timely paper, asked the question, are the ultra-high redshift galaxies surprising in the context of standard galaxy formation models? This is what we show you. And I have a little laser. That's the laser button. Here, nice. So you can see the cyan line is our old model using extended pressure spectrum merger trees, and then these are the new model, which I'll tell you what changed under the hood. and they don't line up exactly, but they are in good agreement with observations still at lower redshift. But out at redshift 11, you can see they have quite some discrepancy. I know it doesn't look like a lot, but this is 8 orders of magnitude in a tiny little panel. So the discrepancy is there, and in redshift 13, we are missing all of these bright stuff. So sort of can't accept it, but let me tell you what changed under the hood. So instead of using extended press structure merger tree, I ran this suite of simulation for graph, which stands for gadget at ultra high redshift with extra fine time steps. You see, all these simulations out there available today, publicly available, have limited number of snapshots at redshift 6 and above, and you can't really resolve the merger history of these payloads. But we really need that for the SAM. So I took matters to my own hand, and I saved 170 snapshots from redshift 6 to 40, which probably is the best merger tree for this purpose. So here you see we have a suite of 4 tiered boxes going from 5 megaparsec to 90 megaparsec, and together they give the state-of-the-art mass function that covers extremely wide mass range. So if you use the Halo mass function for your work, I encourage you to adopt it. So we think the Halo mass functions are fine. If you look at the scalar mass function, they are actually producing a little more galaxies than we used to with extended press structure, which I think because we are now resolving all the merger activities that we don't used to resolve with extended press structure at these redshift, and we didn't do anything out of redshift 11, so we don't have a comparison out there. But the scalar mass function tells us that these bright galaxies are there, yet the luminosity function we showed went under. So should have caught this back in 2022, I suppose. And what's even more puzzling is this quantity called script K. It's not script K is the ratio between UV and SFR, and so it's going above. So these lines mark the canonical value from either Kennicott or McDowell Dickinson. You know, the conversion value from SFR, starvation rate, to UV. If we go above that, that means we're getting fewer UV per SFR. And we go below, we're getting more UV per SFR. So as you can see, the predictions from our model now go above, meaning that we're getting less UV out of the same amount of SFR. That means our galaxies, despite they are at redshift 11, more matter poor and younger instead of age, they are producing less UV per SFR. That's strong. So didn't caught that back in the days. But that raised enough suspicions that I have to launch a full-scale troubleshooting on my own photometry code. And let me just jump to conclusions here. After a month and a half of testing everything, stress testing the code, throwing crazy scenario at it, even rebuilding the whole thing now, the code is 10 times faster, but the good news is there was no bug. The code does exactly what it advertised to do. It does everything correctly. So now I'm going to tell you what went wrong. What went wrong. See, in the past, when we store star formation history with a Santa Cruz SAM, we already know what the output redshift of the galaxy would be, so we can just call that stellar age of 0 year. And then we populate stellar masses for these age bins following what was already set with BCO3. So we already know the output redshift, so we can just dump stellar mass in this without having to worry about at what point are we going to observe the galaxy. But in the post-2022 runs, we did a little upgrade or restructure of the code because we want to be able to mock observe a galaxy at any time we want. So that we store stellar population as a function of the age of the universe. So going from the first bin, 0 to 10 million years, second bin, 10 to 20 million years, in the age of the universe, all the way down to 8 billion years. And then with this setup, we can pick any output redshift we like, mock observe a galaxy and generate photometry. We can even follow its evolution in ionizing photon production history or UV variability. So this is how we do it. We pick any output redshift and then we turn it into a stellar age grid by reverting it. And this is all good with good intention, but what I realized is how NUV changes with stellar age. You can see we go from 1 million year to 10 million year within the first bin. magnitude dropped by 2.5, almost magnitude. So UV luminosity magnitude. So basically, if I lump everything together and call it 5 million years, all the galaxies would be fainter. So if we do this correctly and bin galaxies in 1 million year bins, the purple shift over to the red, and now our luminosity function goes above the old model by roughly the right amount compared to the scatter mouse function, and it should be fine. If I put the observational constraints back in, you can see our red is completely covered by the observed galaxies. Set my Q to N. Anyway, so even at redshift 12, this is fine. I only have time to do my biggest box, so I still have to calculate the rest of the draft boxes, 35, 15, and 5. You can imagine if they go out a little bit, it won't be that far off from these observational constraints, and these are also touching the tail end of it. We might still need to update our star formation model, but the discrepancy might not be as big as we thought. So this is where I stopped showing the old model, and we'll add that. This is what happens if we store star formation history in 1 million year bins. If we continue to actually regrid them to match the BPAS native SAP grid, which a lot of galaxy simulations do, they interpolate their star formation history onto the BPAS grid. The galaxies are even brighter. So the lesson learned here is, it turns out the predicted UV luminosity are very sensitive to how we do the SED model. And these approaches are all valid, except for the first one we did. 10 million year bins are too big. But grouping scatter population into different age bins, how big the age bins are, do we interpolate SED? It makes a huge difference. So back to this plot here. Oh, not that. Well, I also fixed KUV, so galaxies are now brighter instead of fainter. Back to this plot. In all this discrepancy, the first thing came to mind really is, how are the physics different among these models? How can we fix that by changing the physical models? But maybe a lot of this discrepancy are coming from the way we do SED modeling. Maybe if we come to a way to do it robustly and not breaking the bank, then we go down compared to the physics. But there's a lot of noise here that we didn't fully understand and appreciate. So the rest of the paper that we put out was actually still valid. These are things that we looked at in physical space. So just to quickly recap in that paper, what we found is there are plenty of halos, so the universe didn't break. I think lambda CDM still works. And the galaxies at redshift 11 are cooling quite fine, so there is enough cooling, and star formation is quite efficient as well. So if we give it enough time, it can form stars, turn all the gas into stars. But what the problem still exists and is still valid here is that we think feedback is still way too strong. So feedback constantly blow out all the cold gas in our galaxy. And what we're seeing here is really just the one generation of star formation that's formed in the last few time steps. And we don't think that's right. So we probably still need an alternative star formation or feedback model to explain the galaxies that we observe. But in addition to that, I think we need to think more about how do we do the SED modeling. All right, I'm going to stop here. Thank you.
Thank you very much, Harun. We have one question, and in the meantime, the next speaker can come to present.
We've heard other speakers say that burstiness is the key to reproducing the UV luminosity function. What do you do about that in the Santa Cruz SAM?
We tried. So we actually add in a artificial scatter to the UV and turn them into UV luminosity and see, or add a scatter into SFR and turn it into UV and assess how would that boost the luminosity of galaxies or boost the luminosity function. So so here, from left to right, we examine with a artificial scatter with sigma 0.51, 0.52 added to the star formation rate, and then we see how would that boost the luminosity function. So at that time, with the baseline model, we think we need certain level of scattering to get these predicted luminosity function to match observation. So you can imagine if the Z11 luminosity function is already out here, then we probably don't need that burstiness to explain this. And in addition to that, we also asked a bunch of questions. What is needed for the predicted luminosity function to match observations? is cosmic variance that is still pretty much underreported by all these observations. Remember, these JWST fields are pretty tiny, so we can expect some level of cosmic variance among these fields. And then top-heavy IMF can also boost galaxies and make them brighter across the board. And then there's also redshift uncertainty. So a lot of these luminosity functions are made with galaxies across a wide redshift range. Some of them go from 9.5 to 12.5. So the redshift 12 luminosity function looks like this. The redshift 9 luminosity function looks like this. So they really span a huge range. And it really depends on what galaxies we're talking about.
Thank you, Aaron.
Right.
Okay, let's move to the next talk. Thank you again.